In this video, we look at an interesting problem from section 5.4. Chapter 5 is about transcendental functions, and section 5.4 in particular is about exponential functions of base e. So basically, we're revisiting some of the concepts and techniques from earlier in the semester, but now we're applying them to functions that involve exponential functions. This is actually a modification of one of the problems from the book. They're given f of t is the integral from x equals 0 to x equals natural log of t of the cosine of e to the x with respect to x. Now this is going to represent an area or a net area between this function and the x-axis. And we'll draw some pictures in a minute just to get some sense of what that represents. And we're asked to compute f prime. And then we want to represent f prime and f of t visually, and we want to interpret that changing that area visually. And so here's the idea. F of x is our integrand. That's cosine of e to the x. Now, when x equals 0, we get cosine of e to the 0 or cosine of 1. Now, I don't actually know what that is without using a calculator, but using the calculator earlier, I saw it was about 0.54, if I'm remembering correctly. So our graph is going to look like this. Now, the cosine function, f is a cosine function, right? It oscillates between -1 and 1. So our graph is going to look roughly like this, going to hit those maximum and minimum values of -1 and 1. But at 0, we get about 0.54. And then this function is 0 whenever whatever's inside the cosine function is an odd multiple of pi over 2, because that's what cosine of x does. It's equal to 0 at all the odd multiples of pi over 2. We know all the interesting things happen at 1/4 of the period. It starts at its max of 1. Then it goes to a 0. Then it goes to its min of -1. Then it goes back to 0 and then to its max. And this pattern repeats. So it goes max, 0, min, 0, max, 0, min, 0, max, 0, min, 0, max. And it just continues in that way. And again, all of the zeros occur at odd multiples of pi over 2. So this function repeats itself a lot. This is y equals, I'll call this theta. Y equals cosine of theta. And here, instead of a theta, we've got an e to the x. So this function, f of x, our integrand, will have zeros. When the function inside that cosine function is an odd multiple of pi over 2. So we'll say that's pi over 2 times, well, n, which is an integer. If we double it, that makes it an even integer. If we add 1 to that, it makes that an odd integer. So these are the odd multiples of pi over 2. And then if we solve for x by taking the natural log of both sides, we'll have zeros for the integrand when x equals natural log of those odd multiples of pi over 2. So specifically, we'll have x equals natural log of pi over 2, x equals natural log of 3 pi over 2, x equals natural log of 5 pi over 2, natural log of 7 pi over 2, and so on. It'll continue like that. Now we're going to look at this graph on Desmos. One of the things that we'll see is that the natural log of pi over 2 and the natural log of 3 pi over 2 are farther apart than the natural log of 3 pi over 2 and 5 pi over 2. And these two are farther apart than these two are. So the distance between the zeros shrinks as we go from 0 to 0 of this function. So we have kind of a large interval between those zeros there, but then it gets a little bit smaller. And then we've got natural log of 5 pi over 2. And it continues in this way. And the function values are still oscillating between -1 and 1. And that's roughly what it looks like. Now, the integral that we're talking about is this integral from 0 to natural log of t of this function. Now, before we talk about this function f of t with a natural log of t as the upper bound, I'd like to talk about a simpler function. Instead of having a natural log of t inside, I'd like to just have a t inside. So I'm going to call that function capital G of t. It's the integral from 0 to t of cosine of e to the x dx. So x starts at 0, so that's our right bound. And then x ends at t. X equals 0 is actually the y-axis. X equals t is a particular number. And we're going to let t increase at a constant rate. So we're going to imagine that right bound going to the right, just at a constant rate. So I'm thinking of it like almost like a wall, and it's just going to the right at a constant rate. It's hard to make my hand move the constant velocity, but that's the idea. Just moves to the right at a constant rate. And then this g of t is actually calculating a net area. It's looking at the area bounded by this function, f of x equals cosine of e to the x, and the x-axis. And whenever that function is positive, it's counting that area as positive. And whenever the function is negative, we're actually subtracting an area. So when I say that this represents the net area, between the graph of the function and the x-axis. What I mean is we're going to find that area that's bounded by the function in the x-axis, but if it's above the x-axis, we add it, and if it's below the x-axis, we subtract it. So on the integral from this x equals 0 to this particular t, the value of g of t will be this area minus this area plus that area. So it's between the graph of the f of x and the x-axis. In the vertical lines, x equals 0 and x equals t. Now, one thing I want you to notice is that as we move that vertical line, x equals t, farther and farther to the right, at least on this interval, that area under the curve is going to increase until we get to this first 0 of f of x. So what we'll see is that the area is initially 0, because if I evaluate this at t equals 0, I've got g of 0 is the integral from 0 to 0 of cosine of e to the x dx. So we're just finding the area under a point. So there's no area there, so it's 0. But then our area is going to increase until we get to some particular value. And then at that point, we start subtracting area. So our area will decrease. And then at the point where this area is, or this area under the x-axis is equal to the area below the x-axis, g of t will equal 0, whatever that value is. And then we'll continue to subtract area. We'll subtract area and subtract area and subtract area until we get to some value here. And then at this point, our g of t function, that net area function, will have a relative minimum. And then we'll start adding areas. And so the graph might look like this. And we would keep adding area until this area and this area are the same as this area. Then we'd have a 0. And then if we continue to add area after that, the function would continue to increase. I'm not actually sure if this area plus this area is greater than this area. If it is, there would be some x value in between where the function is 0. If not, then the g might actually have a relative max at this point. But the point is that we keep adding area until we get to this point, and then at this point we start subtracting area again. So our g function is going to have a relative maximum. Let's say that this area plus this area eventually exceeds that. Then our function would look like that, and then at this point we would start subtracting area again. And so it would look like that until this point. And then we start adding area, so the function increases. And then we start subtracting area, so the function decreases again. And in that way, like that's what our g of t function looks like. So that's our net area function. Okay, so now we want to compute g prime. Now the way we compute g prime is using the second fundamental theorem of calculus. Now, this is using slightly different notation than we use in the book, but I want to make my notation consistent here with this function that we have here. So let's say let g of t, the integral from a to t of f of x dx, where f of x is continuous on the interval from x equals a to x equals t. So we've got a nice smooth curve, and then this integral represents that net area under the curve. Area above the x-axis minus the area below. Then g prime of t can be written in Leibniz notation as dg dt. That represents the rate of change of that net area function. Sometimes it's called an accumulation function because we're accumulating area under the curve with respect to time. And it's positive when f is positive, it's negative when f of x is negative. That rate of change turns out to be that f of x. Or actually, excuse me, it's not f of x, it's f of t. So this is going to be some number of units of area squared, or so it's units of length squared per unit time. And f of when xt is positive, g is increasing. So the net area function is increasing, which just means that we're adding area. And then when f of t is negative, then we're subtracting area. The net area is decreasing. Which is what we see here. We say, okay, this when f is positive, we're adding. Then at this point, we start subtracting area. And then at this point, we start adding area again. And then we're subtracting. And then we're adding. And it continues to go like that. So that's what the second fundamental theorem says. If you have a function or if you have an integral function that is an integral from a constant to t of f of x dx, the derivative of that is just the integrand, but instead of having an x inside, you're going to have a t. And this is going to be some number of units squared per unit time if we're interpreting it geometrically as area or net area under the curve. So for this particular function, g prime is just cosine of e to the t. And then that's gonna be unit squared of area, or unit squared, those are units of area per unit time. If our area is being measured in inches, or if our distances in the x direction and y direction are measured in inches, and our time is measured in seconds, this would be some number of inches squared per second, and it might be positive or negative. It'll be negative when our function is below the x-axis and positive when our original function, that integrand, is above the x-axis. Okay, so let's look at this visually. One thing I want you to see when we represent this visually is we're going to let x change with time, and we're going to let that value of x, that vertical line, just move to the right at a constant rate. So if I take the derivative of x with respect to t, x prime is just 1. That's 1 unit per unit time. I'm actually not sure how many units we are moving to the right per unit time when we use the Desmos app to sort of let t increase for us, but we know we're going to move to the right at a constant pace. Another thing that I want you to notice is that as our x value, or our rightmost bound for that sort of net area function moves farther to the right, we're moving at a constant rate, but that x value is passing these zeros of the original integrand, which represent relative maxima, relative minima of that area function, sort of on like intervals that are not evenly spaced. The distance between these two zeros is larger than the distance between these two zeros, which is larger than the distance between these two zeros, which is larger between the distance between the next two zeros, and so on. That pattern continues as t goes to infinity. So we're going to look at that. And then after we do that, we'll change our perspective and think about the original function. So just a note, this is based on exercise 53 from section 5.4 of the Larson calculus text, Larson calculus 10th edition. If you want to find the original problem, you can find it there, but I've modified it. I've changed some of the variables, and then I've added this request that we represent and interpret the changing net area or accumulation function visually. Okay, so this is the function we're interested in. But first, rather than looking at that function, we're going to look at this g of t, where g of t is the integral from 0 to t of cosine of e to the x dx. So cosine of e to the x is this TL function. And as I said, the zeros are sort of far apart at first, and then they get closer and closer together as t increases. If we zoom out, that's what it looks like. Now, the y values are always between -1 and 1, because this is f cosine of e to the x. So that cosine values still oscillate between -1 and 1, but they're oscillating faster and faster between -1 and 1 as x goes to infinity. So as x gets larger and larger, those zeros are closer and closer together. All right. So let's graph that area function. So when we integrate from 0 to 0, we get 0 for our area function. And then we have a maximum at this natural log of 1/2. And let's see, what is natural log of 1/2? Or I said natural log of 1/2. I meant natural log of pi divided by 2. So 0.45. So 0.45158. That's the same as this number here. That's where the integrand is 0, so the rate of change is 0. And then the that net area function is at a relative max, because at that point, instead of adding area, we start subtracting areas, because the original function starts to be negative. And we're subtracting area until we get to natural log of 3 pi over 2, which is at 1.55. And so we have a relative minimum, and then we start adding area again, so the net area function starts to increase. And the way I've drawn this, or had Desmos draw it, I let my upper bound be x equals t, and we're going to let t increase at a constant rate. And I added these horizontal lines, y equals 1 and y equals -1 for emphasis, just to remind us that we really are achieving that value of -1 and 1, and the function's oscillating between -1 and 1 more rapidly as x goes to infinity. Now let's see what happens as t increases from 0 to 7 pi over 6. So we were adding area, and now we're subtracting area, so the orange function decreases. We're subtracting area, now we start adding area, so the orange function increases. And we start subtracting area, so the orange function decreases. Then we're adding area, subtracting area, adding area, subtracting area, adding area, subtracting area, adding area, subtracting area. And we see it happen sort of faster. But if you focus on that pink dot on the x-axis, notice that we're moving across the x-axis at a constant rate. I don't actually know what that rate is, but it's a constant rate. We took the derivative of x equals t, we just get 1. So 1 unit per unit time. I just don't know what those units are. I think it's kind of cool. I like looking at this graph. And then the rate of change of that area function, that net area or accumulation function, is just the integrand evaluated at t. So it makes sense that g prime of t, that's going to be some number of units of area, so units squared per unit time. It's positive when the original integrand is positive because we're adding area, and it's negative when the original integrand is negative, or the integrand is negative because we're subtracting area. But again, as we see this graph, as we look at this graph and we graph more and more area, letting that vertical line move to the right, we see sort of how that area is changing with time. But that vertical line is moving to the right at a constant rate. All right. So now we're going to change things up a little bit. Rather than moving to the right at a constant rate, we're going to let our x value change according to the function x of t equals natural log of t. So now we've changed it a little bit. We're going to let f of t equal g evaluated at natural log of t. So instead of having an upper bound of t, we have an upper bound of natural log of t. Now the graph looks almost identical to what it was before. I have graphed the y-intercept of the original function, and the integrand is cosine of 1, which is 0.5403 approximately. And we've got again, a maximum of 0.45, or excuse me, at x equals 0.45, which is approximately a natural log of pi over 2. Or natural log of pi over 2 is where the 0 is, which is approximately 0.45. I said that backwards. And the net area is 0.1346. So that area from 0 to natural log of pi over 2 is equal to that 0.1346. And then we start subtracting area. So one thing I want you to notice, if I let my upper bound equal natural log of t, is that natural log of t increases very rapidly at first in the vicinity of t equals 0. Because that natural log of t has a vertical asymptote at x equals 0 or t equals 0. And the slope is 1 divided by t. So if our t value is very, very small, we're taking 1 and we're dividing by a very small number. So we're going to get a very large number. We get a very large positive slope. So what that means is geometrically, it's a large positive slope. But when we think about it, the rate of change with respect to time, that is a very large number, a very large change in x as time changes. So we're moving to the right at a very fast rate. But then as t increases, that 1 over t continues to decrease. So we're going to continue to move to the right. We're just going to move to the right slower and slower and slower. So let's look at that. So we're moving to the right. It's very fast at first. And then notice we sort of slow down. And we slow down a bit. And we slow down. Okay. So let's look at that one more time. Again, essentially, it goes, our point is moving, our vertical line is moving very, very quickly to the right. And then it just starts to, it continues to move to the right, but just at a slower pace. Now, spatially, we mentioned before that the zeros between, or the zeros of the integrand are not evenly spaced. They're larger at first, and then they get smaller and smaller and smaller and smaller and smaller. So that's happening, but temporally in time, they actually are evenly spaced because we actually achieve, or the x value passes this first 0 at t equals pi over 2. And then pi over, or pi seconds later, pi units of time later, we're at this 0. Then pi units of time later, we're at this 0. And then at this 0, pi units of time later. So the function, the x value is actually passing that 0 every pi units, like starting with that first zero, as pi units of time, but it's actually slowing down as it goes from 0 to 0. It's almost like it's hesitating as it's going from point to point. But it hits those zeros on the same, like on a regular basis at the same time. Like it's almost like a metronome. So it goes to the 0 and then the 0. I'll try to do it. The 0 and then the 0 and then the 0 and then the 0. I'm actually kind of messing up the tempo myself, but that's the idea. These bases are farther apart in x, but they're the same distance apart in time. So our velocity is actually sort of decreasing because the change in position per unit time is a smaller number divided by that pi units of time for every subinterval. Okay, well, now let's actually compute the derivative of f of t. We'll compute the derivative of f of t using the chain rule. We'll do that on paper, and then we'll try to interpret that geometrically. So f of t is the g evaluated at natural log of t. That's the integral from 0 to natural log of t of cosine of e to the x with respect to x. Now, when we take the derivative of this, we take the derivative of the outside function first, evaluated at the inside function. And this is our inside function. Now, according to the second fundamental theorem of calculus, the derivative of something that looks like this is just the integrand evaluated at t. So when I see a function of t here rather than just a t, I know the derivative of the outside is just the integrand evaluated at this inside function. So it's again the derivative of the outside evaluated at the inside times the derivative of the inside. And the derivative of natural log of t is 1 divided by 2. So what we end up with is that the f prime is cosine of e to the natural log of t times 1 over t. Now, e to the natural log of t is just t, because the exponential and the natural logarithm are the same base undo each other. And so that's just a 2, or not a 2, just a t. This ends up being cosine of t divided by t. So f prime is going to equal 0 every time cosine is 0. So f prime equals 0 when t equals pi over 2, 3 pi over 2, 5 pi over 2, and so on. So rather than equaling 0 at all on those intervals that aren't evenly spaced with the natural log of pi over 2, the natural log of 3 pi over 2, the natural log of 5 pi over 2, and so on, this rate of change is equal to 0, starting at pi over 2 and then every pi unit thereafter. So we get that. So that means our area function achieves relative minima and maxima. It's a relative max, then a relative min, then a relative max, then a relative min, and so on. So f achieves, let's say, relative extrema. I want to say at evenly spaced time intervals, but and I'll just say it, t equals pi over 2, 3 pi over 2, 5 pi over 2, and so on. And how do we interpret that? Well, this is the change in area, some number of units squared with respect to time. And this will be f prime of t will be positive whenever cosine of t is positive and negative whenever cosine of t is negative. So cosine of t actually looks like this. All of those zeros are evenly spaced. So the derivative will be adding area, then subtracting area, then adding area, and then subtracting area, and adding area, and then subtracting area. So that will determine the SIGN sign of that f prime of t. And so those zeros occur at those evenly spaced time values. But that rate of change on intervals as t goes to infinity actually decreases because we're taking this number, which is between -1 and 1, and then we're dividing by t. So on this interval, when we divide by t, we're dividing by something that's relatively small. But when we get out here, our t values are relatively large. So we've got some number between -1 and 1, and when t gets larger, then this fraction gets smaller. Okay, so now we know that this is the change in net area, or the change in the accumulation function with respect to time, which is giving us this. So now we know that the zeros occur at these evenly spaced time intervals. But visually, we know, like spatially, those zeros are not evenly spaced. The distance apart is decreasing. The distance from this zero to this zero is greater than this distance from this one to this one, which is greater than the distance from this one to this one, which is greater than the distance from this one to this one. So the distance between consecutive zeros is getting smaller, but the time that we get to those zeros is evenly spaced, again, because it's like our x coordinate keeps moving forward, but it's slowing down as it moves forward. Now, with that in mind, I think we have computed this derivative using the chain rule and the second fundamental theorem of calculus, so that's good. We've interpreted it in terms of that sort of net area function and how it changes with time. We could also use a change, or we could also look at this in terms of a change of variable. So this says start at x equals 0 and go to x equals natural log of t and see how that area under the curve changes with time. Well, this is what we get. This is how it changes with time. You say, well, there might be another function that changes, or another integral that represents the same net area. And we can find that if we do a u substitution. So let's do a u substitution now. We've got f of t equals the integral from 0 to natural log of t of cosine of e to the x dx. And we computed f prime. We got cosine of t dt, or it's a cosine of t divided by t, sorry. That's units squared per unit time. And we're going to use the u substitution here. We're going to let u be that inside function. Then if u is equal to e to the x, then du is e to the x dx. But e to the x is actually u. So this says du is u times dx. So if I want to, I can get dx by itself by dividing both sides by u, or multiplying, or dividing both sides by u or multiplying by 1 over u, same thing. So we see that this is cosine of u times dx, which is 1 over u du. Now, we also need new upper and lower bounds. These are x values. This says x starts at t and x ends at 0. I'll say, well, where does u start and where does u stop? Well, we can find that by evaluating u at the upper and lower bounds for x to get the new upper and lower bounds in terms of u. So the upper bound for x was x equals natural log of t. When x equals natural log of t, u is equal to e to the natural log of t, and because the exponential and the logarithm undo each other, because they're inverses, we just get a t there. And then when x equals 0, u is e to the 0, which is 1. So this integral from 0 to natural log of t of cosine of e to the x dx is equal to the integral of cosine of u times 1 over u, so there's a u in the denominator, du, from u equals 1 to u equals t. Oops, t. Now, because u is just a dummy variable, we're integrating with respect to u here, we could change that. We could call that theta, we could call that y, we could call that any number of variables that we want. because we're used to representing our integrands as function of x, we'll say that this is the integral from 1 to t of cosine of x divided by x dx. And that will be the same value. Now, when we interpret this in terms of motion, in terms of that changing area with respect to time, it's not going to be exactly the same because that upper bound is equal to t. So we're having x equal to t again. So our x value is increasing at a constant rate here, whereas over here, our x value was always increasing, but the rate of change of that increase was decreasing. So it's like we're always moving to the right, but we're always slowing down. Here, we're always moving to the right at a constant rate. So let's visualize this. Basically, what we're going to see this time is that instead of having an integrand that is always between -1 and 1, which this one is, and this one oscillates rapidly between -1 and 1, we're taking a number that oscillates between -1 and 1 and we're dividing by x. So there's some damping there. It sort of damps out, and as x gets very large, that integrand gets smaller. So I don't actually know what it looks like. Cosine is 1 at 0, and then we're dividing by a tiny positive number. So I'm going to have a vertical asymptote here. And then at pi over 2, cosine is 0. And then at pi, we'll have -1 divided by pi. So -1 over pi is 1/3, or -1/3. So let's say that this is +1 and this is -1. So I have a -1/3 there. So I'll have something like that. And at 3 pi over 2, our function is 0 again. And then at 2 pi, we'll have cosine of 2 pi, which is 1 divided by 2 pi. So it's like pi, or 1 divided by 6, so 1/6. But we continue in this way, and one thing I want you to notice is that the zeros are evenly spaced now, spatially evenly spaced. But the area under this curve and the area under the corresponding curve, this one over here, it turns out we get the same areas either way. And with this one, we're integrating from x equals 1 to t. This is pi divided by 2 is about 3 divided by 2, so it's about 1.5. So we actually start at 1 when we start integrating. When we compute that area, at x equals 1, we get 1 cosine of 1 here. On this one, when x equals 0, we're evaluating at x equals 0 cosine of e to the 0, so cosine of 1 as well. So we start looking at the area under the curve. And again, we're looking at a net area, starting at x equals 1 and going to x equals t. And it's this area minus this area. But what we'll find is when we take the derivative of this with respect to t, well, we get the same derivative. The derivative of this with respect to t is the integrand, but instead of evaluating it at x, we'd evaluate it at t. So we still have that same derivative for this function that we had for this function. So let's look at this again. T goes from 1 to e to the 7 pi over 6, as x goes from 0 to 7 pi over 6. So our x value is moving to the right, but it's moving more slowly. But it's passing those zeros temporarily every pi units of time. Pi units of time, function increases, then pi units of time later, passes a 0, then it passes a 0, then our function passes a 0. But the accumulation function, that area, is increasing when the function's positive, and then passes 0, so then it's suddenly decreasing, and then it's increasing, and it's decreasing, and so on. So that's how that works. We say, okay, well, what happens after we change the variables? Now remember, this is the one where our function is always oscillating between -1 and 1. But after our change of variables, our integrand looks a little different. It looks like this. So here is f of t, and the integrand is f of t equals cosine of t divided by t, or alternatively, we can think of this as cosine of x divided by x. And we're integrating from x equals 1 to, I think it's like 23 pi over 2, something like that. Having a little bit of problems with my code. That should be an x. Sorry. There we go. So now let's let t increase from 1 to 23 pi over 2. One thing I want you to notice about the y values on the graph of cosine of x divided by x is, again, we have that damping because as x goes to infinity, that we've got a number that's oscillating between -1 and 1 divided by a number that's getting larger and larger. That fraction sort of gets smaller, but we just keep getting closer and closer to that x-axis. So that's what we see. But if we actually look at the function values for that area under the curve, we're going to see that the areas here are equal to the areas that we got in this problem. So let's like zoom in a little bit. I think I said like, sorry. So if we look at that first interval, look at that first 0 of the function. I don't want to lock my viewpoint. I want to zoom in a lot. So that first 0 occurs right here at pi over 2 now. Because of our change of variables, the zeros of the function occur at all the odd multiples of pi over 2. Instead of the logs of the odd multiples of pi over 2, it's just at the odd multiples of pi over 2. So we get at that first 0, we are adding up all that area, that purple area right there. And the y value there at x equals 1 is 0.54. If we look at the corresponding y value over here, we have a y value of 0.54. As we integrate from 0 to natural log of pi over 2, the area achieves a maximum of 0.1346. If we go over here, that area still achieves a maximum of 0.1346 approximately. And then as we let t increase, I think I want to slow it down just a little bit. We're adding area at first. Then at this point, we start subtracting area. So our area function, that's the blue function now, starts to decrease. Now, if we look at the y value there at that 0 of our integrand, we have this area, this purple area minus this purple area. That net area is negative because this area is larger than that area. It's a negative 0.5358 approximately. If we go to this one, we go to our second 0. Oops. It's hard to get it on exactly where we want it to be, isn't it? That second 0 occurs at this negative, or at what is it, natural log of 3 pi over 2. And the net area is this purple area minus this purple area. So we get that negative 0.5358 again. And then the next maximum occurs at natural log, that was natural log of pi over 2, natural log of 3 pi over 2, then we have natural log of 5 pi over 2. So we're adding area from here to here. So because of that function, that integrand being positive on that interval, after we add area, we don't add enough to get back to 0. The net area is still negative because this area is larger than this area plus this area. The net area is that negative 0.2136 approximately. Now, after the change of variables, after the first 0, we've got an area of 0.3146, which is what we got on the other graph. After the second interval, where the function is negative the entire time, our net area function is that negative 5.358 approximately. So we have the same value there. And then if we keep going to that third zero, well, then we're going to have a relative max for the area there because we've added area. We're adding as much as possible. And then we get to that relative max, which is approximately that negative 0.2136, or 36 is the actual value. And I think I'm approximating it with this one. But it's because we're adding area and then subtracting area and then adding area and then subtracting area and so on. And you might say, well, that graph looks different from the other graph. It does. The other graph oscillates between -1, and with this graph, the oscillations are getting closer, or the function is still oscillating, but it's getting closer and closer to 0. But with, I'm sorry, excuse me, I'm sorry. But my point is, even though the y values are decreasing on this graph, the area under the curve here is exactly the same as the corresponding areas under the curve here. The function values are 0 at like with different spacing. We have larger spacing between the zeros at first here, and then the zeros get closer and closer together. On this one, the zeros are the exact same distance apart, but the heights keep shrinking. Since the zeros are the same distance apart and the heights keep shrinking, those areas under the curve, area either above the x-axis and bounded by the x-axis in the function, or below the x-axis and bounded by the x-axis in the function. Whether we're talking about those areas or those areas, the areas themselves are the same. So after we do the change of variables, these areas are equal to these areas. And so the actual areas themselves, the minima and maxima of the areas are the same, even though the x values where those minima and maxima occur are different, because we made the change of variables, because we let u equal e to the x. And then eventually we said, instead of calling u equal, letting this be a function of u, let's let everything be back in terms of x. So we switched back to x from there. But the areas are the same. So I think that's kind of interesting. I hope you like that. Let me know if you have any questions. I think we've successfully looked at that integral for f and discussed it as or discussed the integrand as the rate of change of that net area under the curve with respect to time. And then if we replace that upper bound with a natural log of t instead of a t, we see that rate of change, well, anyway, we've already talked about it. Let me know if you have any questions.